Welcome to the fourth episode of A Visual Approach to Optics, a guide for clinicians, narrated by Dr. John Gorfinkel. In the first three episodes, we covered 79 out of 275 slides. We finished the last episode with this slide showing the eye and ametropia. Here we see a patient who has myopia. In other words, when an object is at infinity, it is focused in front of the retina, too far in front. The rays are converging to a point, and then they diverge so that they intersect the retina, forming a blur circle. In other words, an object point here becomes a blur circle here. However, if we have an object that is close enough to this eye with enough divergence, then the eye will converge the light to a point further back. Because the light starts off with minus vergence as compared to here, the same converging power will result in less image vergence, and therefore an image point farther away. This person can see an object close up at this distance, but not far away. This is called the far point of the eye, and this point is considered to be conjugate with the retina. In other words, in this optical system, a point here will be focused to a point here. This person is called nearsighted because they can see objects at near without glasses, but not far away. It is assumed in this diagram that the patient is in the unaccommodated state, in other words, not adding any converging power to try to see up close. In this diagram, we see that an object at infinity is focused too far posteriorly and intersects the retina before a point is formed. In other words, a blur circle on the retina. If we have rays that are converging sufficiently onto the eye such that the eye will then add its convergence, the image will be now focused further in front on the retina as compared to the upper diagram. The converging power here is the same as here, but because one starts with converging rays, the image vergence is increased as compared to here, resulting in an image further in front. Optically speaking, rays that are convergent have to have begun from beyond infinity, or what is mathematically equivalent, a virtual object behind the eye. In the real world, one does not see converging rays unless there is another optical system in front that has caused this to happen, because light leaving objects is always divergent. In this slide, we summarize the far point of the eye. In this case, infinity is conjugate with the retina, and the far point of the eye is at infinity. In this case, the image or the object here at this distance from the eye is conjugate with the retina. And this is therefore the far point of the eye. Light from further away will be focused too far in front. In this eye, an object behind the eye at this plane is conjugate with the retinal plane. In other words, the far point of the eye is here and is conjugate with the retina. Here we show a correcting lens for myopia. An object at infinity has non-vergent rays that would otherwise be focused too far in front of the retina. but we have placed a diverging lens in front of the eye so that the rays that come out are divergent enough so that when converged by this eye, the sum total will result in less image vergence and an image further back onto the retina. Note that this lens is taking non-vergent light and forming a virtual image on the left side at this plane, which is the secondary focal point of this lens. This point is also the far point of this person's eye and is conjugate with the retina. One can think of this process as the lens creating a virtual image at the far point of the eye, and then the far point of the eye allows a clear image to be formed on the retina in a two-step process. In reality, the light is non-vergent till it becomes divergent, then it becomes convergent and forms the image. But thinking of it in a two-step process involving this virtual image helps understand what is going on. The two stages of refraction of the myope wearing glasses. Object at infinity forms image at the secondary focal point, equals far point of the eye, therefore is conjugate with the retina. This is a summary of the two-step analysis of the correcting lens for myopia, and this is what is happening in the real world. Here we see the situation for correcting lenses of the hyperopic eye, also sometimes called hypermetropic eye. We have an object at infinity, and we have a converging lens that adds convergence so that the image that would otherwise be behind the retina is focused on the retina. This is the two-step mathematical process in which the non-vergent rays are converged by this lens to the secondary focal point of this lens, which is behind the eye, if the eye optics were not there. And this secondary focal point is also the far point of the eye and therefore conjugate with the retina. The overall effect is to have non-vergent light becoming a little more convergent and then more convergent by the optics of the eye to the right degree so that it is focused on the retina. In presbyopia, one loses the ability to accommodate to varying degrees. If we assume that there is no accommodation present here, then an object at infinity is shown to be focused on the retina. In this diagram, the object is closer to the eye, therefore has divergent light, and is now focused by this same optical system too far behind the eye. In this case, we put in a converging lens in front of the eye so that the object at near is then focused more anteriorly and onto the retina. This correcting lens, however, would have to be removed in order to see objects at a distance. Therefore, this person would require one set of glasses without correction for distance and one set with correction for near. These are often combined in an upper and lower segment called bifocals. The reading segment is called an ad. In this slide, we assume that there is no accommodation available to this person. If we have an object a half meter away, the divergence of the light at the lens before entering is -2 diopters. In this situation, the light would end up being focused too far behind the eye. If we add a +2 reading glasses in front to compensate for the -2, then we would turn the divergent rays into non-vergent rays, leaving the glasses, and then entering the eye so that it is focused onto the retina. It is assumed that this person is otherwise ametropic and able to see in the distance without glasses. The divergence of light from near objects varies with the distance of the object from the eye. At 50 centimeters away, the light will have -2 vergence at the eye. If the reading material is 40 centimeters from the eye, then the vergence will be 100 over 40, which is 2.5 diopters of divergence. If the reading material is held 33 centimeters in front, then there will be a vergence of -3. In other words, the closer one holds the reading material, the more reading add is required to be able to see clearly. Printed material or cell phones are typically held at 33 to 40 centimeters away, while computer screens are often 50 centimeters away. Therefore, the reading glasses have to be adjusted appropriately for the appropriate activity. +2 then for the computer screen, or 2.5 for most other close activities. It is assumed in this slide that the patient is otherwise ametropic and sees in the distance without glasses. In the real world, presbyopia is not all or none. In presbyopia, the accommodative amplitude, or the ability to add converging power in the eye, is reduced but not absent. It is reduced in an age-related fashion. Let's say that a person has an accommodative amplitude of 1 diopter. Say this person is ametropic and looking through a +2 diopter lens. If not accommodating, this person can see at 50 centimeters clearly. If accommodating 1 diopter, one can add 1 to the number 2, and one is able to have an extra 3 diopters so that one can see divergent light of -3 diopters. In other words, an object that is 33 centimeters away. This person can see through the reading glasses from 50 centimeters to 33 centimeters, depending on the amount of accommodation. If we remove the reading glass, this patient can see at infinity when not accommodating, and when using accommodation, can see at 1 meter away, 100 centimeters, by using 1 diopter. In other words, without the reading glass in place, the range of clear vision is from infinity to 1 diopter. In the bottom, we see what happens if there's no accommodation available. There are only 2 planes which are clear, either looking through the reading glass at 50 centimeter or without the reading glass at infinity. All other distances would be blurry. In the upper diagram, we see that there is a range of clear vision from infinity to 1 meter and from 50 centimeters to 33 centimeters. But there still are areas between 1 meter and 50 centimeters from the eye which are not clear, and also every place that's closer than 33 centimeters. We often talk about blur circles. In this diagram, we see non-vergent light entering the optical system. It is focused too far in front of the retina. The rays were converging to this point, but then beyond the point start diverging again, and they intersect the retina where they form a blur circle of light. This is the myopic situation. In the hyperopic situation, the image rays would be focused behind the retina if the retina were not there. However, they are blocked and intersected by the retina to form a blur circle. So either myopia or hyperopia will result in a blur circle on the retina. Where object points are represented by blur circles may overlap on the eye so that 2 points on the object are represented by 2 blur circles that are indistinguishable one from the other. This decreases resolution and visual acuity. Here we see an example of an eye with a smaller pupil and a larger pupil. In both cases, the eye is myopic and the image is focused too anteriorly. But where the pupil is small, in other words, the aperture of this optical system is small, only central rays get through and form a smaller blur circle than here, where all the peripheral rays also get through. While there is more light coming through here, there is a larger blur circle. And that is the trade-off in all optical systems. Larger apertures are prone to cause larger blur circles, but do allow more light, whereas smaller ones do the opposite. Our optical system is designed to have a smaller pupil in brighter light and a larger pupil in dim light when we really need the intensity as high as possible. Smaller blur circles approximate a point better, so it looks clearer. Reducing the aperture of an optical system to sharpen an image is called the pinhole effect. Here we see 3 objects in 3 different planes focused by this converging lens onto a plane. One can see that the blue is focused in front. These colors are just for representation only, that the blue is focused in front, the green is focused behind, and the red is focused on the plane. Because the divergence of the light coming from the 3 different object points is different, they end up in different places as image points. There's only one of these in focus, but the other 2 have formed blur circles in the plane of interest. If one narrows the aperture of this optical system, the blur circles can be made smaller and approximate a point better, so that the range of apparently clear view is increased. In other words, the depth of field around the true plane in focus is wider for smaller opening. This is why cameras with small apertures don't need to be focused as critically as those with larger ones. However, those cameras let in less light. Here we show correcting lenses for eye error in ametropia. We described hyperopia as an optical system not sufficient to bring the rays to focus, so that they end up too far behind. In other words, there is a relative deficiency of converging power in the hyperopic eye. In other words, it has an eye error of -2, meaning it is missing, in this example of a 2-diopter hyperopic eye, it is missing 2 diopters of converging power. We could put a correcting lens in front of +2 to compensate for that. We often clinically think of the ametropia in terms of the correcting lens. So when we speak of hyperopia, we say, oh, this hyperope is a +2. But really, the +2 represents the correcting lens. The actual eye itself is deficient and has an eye error of -2. In this case of the myope, where the image would otherwise be focused too far in front, the eye has excess converging power. We say that the eye error is +2, and we need a -2 in front lens to compensate for it. Again, we describe the myope often in terms of the correcting lens and say it is a -2 myope, but in actual fact the eye error is +2. It has too much converging power by 2 diopters in this example. In this slide, we see how an object point is formed into a sharp image point. This image point is known as stigmatic. It is stigmatic because it is sharp. If we cannot form a sharp image point, then we would say it is astigmatic. In this 3-dimensional representation, we see spherical wavefronts of light with the corresponding rays to show their direction of movement coming to a converging lens, and the light is now shown to be converging to a point in this plane. If there's nothing blocking the light here, then the converging light will continue to and now start to diverge beyond the image point. If we were to have converging light coming to an image point here, but we put a screen here, the screen will interrupt the light before it has had a chance to converge to a point. The object point here is represented by a blur circle in this plane. If there were 2 object points close together here and here, then there would be 2 overlapping blur circles, and resolution would be lost, and the image would be blurred. We could move the screen here back to this plane where the image is stigmatic to see it more clearly. If we were to move this plane or this screen further back here, once again we would have blur circles. One can see here that if the screen were in this position, the blur circles would be larger than in this position. As we get closer to the plane of the image point, the blur circles are smaller. And then as we go further behind, the blur circles start to get larger again. If we placed an aperture in front of this lens, in other words, to block the peripheral part of the wavefronts, only letting the central part through, we would see smaller blur circles. The grayed out dotted lines and circles show the light that is now blocked by the aperture margins. And only the central and paracentral rays get through, so that the blur circles are all smaller. Ever wonder what would happen if the aperture were not round? Here is a square aperture. If we then put the screen at this plane, we would see blur squares representing object points. The blur squares would be of different size as we get closer, and they get smaller as we get closer to the image point. Note that once we reach a point, it is the same point no matter what the shape of the aperture is. One just sees the aperture shape when away from the point of maximum clarity. Up until now, we described spherical lenses, which converge or diverge light in all planes equally. Cylinders, however, only have power to change vergence in one axis. Here we have an object point, and there's no lens in place. Light is just diverging in every axis and lighting up this plane here, or this screen. Here we show a cylindrical lens, which has no curvature in the vertical axis, but has convex curvature in the horizontal. In this case, we show a converging lens in the horizontal, but no lens power in the vertical. In other words, light that spreads out in the horizontal plane will be brought back together to a point. But light that spreads out in the vertical plane is unaffected. The effect is to give a vertical line instead of a point on the screen. The line is typically parallel to the long axis of the cylinder, as shown here. If we then take two cylinders at 90 degrees to each other of equal power, we have then now converted this back again to spherical, and now we bring the light both horizontal and vertical to a point, and we're back to where we were in earlier slides. Here's another representation of light across the horizontal in different levels of the cylinder. The horizontally spread light is brought to a focus, is compressed horizontally at different levels, and when done at every level, there are many different points which form an image line. Here's another way of showing different rays and how they get bent inwards in one axis only, forming the image line. The nomenclature of cylinder axis is as follows. We draw a line horizontally to the right and then go counterclockwise to the long axis of the cylinder, and that will be the number of degrees. We can go up to 180 degrees. If we go 190 degrees here, then that is just the same as 10 degrees here. So we only, because it is one axis, it's a cylinder axis. So we only need to talk about 0 to 180. So here we show light entering a cylinder oriented horizontally. The long axis is horizontal, but the curvature is vertical. In other words, the power is in the vertical meridian. Along the horizontal axis, there is no power because the lens is flat. The light that goes through this lens is compressed in the vertical direction, but not in the horizontal. And so it's compressed until it reaches a line, and then it diverges out again in only one meridian. One can think of this as a horizontal trapezoidal prism of light, but at the middle it forms a horizontal line. Similarly, a vertical cylinder will form a vertical line and vertical trapezoidal prisms of light at different distances away. Here, these trapezoids are being compressed till they reach a line in that there is no width horizontally, and then they start expanding horizontally once again. Here we see what happens when we have two prisms of different powers at 90 degrees apart. In this particular drawing, we assume that the horizontal prism has more power than the vertical prism. We see that the light is being compressed in the vertical direction by this horizontal prism faster than the other axis. In other words, we get ovals that shrink in the vertical until it forms a horizontal line. At some point, it starts to expand again. We can see that at this point, the weaker vertical cylinder has finally converged the horizontal axis until there is no horizontal distance, only a vertical line remains, and then it starts expanding beyond that. We have the horizontal line here created by the horizontal cylinder, and we have the vertical line here created by the vertical cylinder. This is called Sturm's interval. Somewhere in between these two, we have a shape, a cross-sectional shape of this whole blob of light, which is a circle. It turns out that this is the best place to put on a image plane, such as the retina, in order to see it clearly. It is best that the retina would intersect this circle of least confusion than it would be to have it intersect this conoid of light at any other point. The circle of least confusion is typically in between the two lines. It's somewhere in Sturm's interval.